Hello, my name is Igor Sadalski. This year I was a serve in Amber Lab under supervision of Noel Kosmak-Shanklin and Professor Aaron Ames. I was working on a non-linear model predictive control for a 3D hopping robot. To begin with, the problem we try to address in our research is how to create a control policy that will be less computationally expensive. For this, we use a Hopper hardware platform. Hoppers have played a crucial role as a testbed for new control algorithms since the beginning of the robotics community. In our case, this hopper, which is roughly the size of the real one, consists of two main elements. Those are the reaction wheels that allow us to change the orientation of the robot while in motion, as well as the spring that allows it to jump. When it comes to the architecture of our model predictive control itself, on a high level, it consists of communication between the physical robot and controller block. We use controller block called MPC, or model predictive control, which consists of three main parts. First, it is a high-level controller that generates a desired trajectories that we wish to follow. Secondly, it's a finite time optimal control problem. It takes the model of the robot and next runs the optimization problem to generate the optimal state and torque commands. These are next fed into the interpolator block, which is able to create torque commands at a more high frequency than the optimization block, which are next converted into current and fed back into the robot, which closes the loop. One of the novelty that we use to create this reduced computational complexity solution is to incorporate hybrid dynamics of our robot into the model predictive architecture. In our case, we are able to distinguish between different phases of the motion. For example, when we are on flight or when we are on the ground. Once in flight, we are able to use the reduced order model, and thus it requires less computational costs. In specific, we are using actuated coordinates to exert and move our under-actuated ones. After running this controller, we were able to verify it and test it in a simulation. We use a simulator called Mujoko. Next of all, we move to the hardware implementation. Since our robot requires optimization and solving of a convex optimization problem, we needed to use an external computing platform. To do so, we connected to it using the wireless Wi-Fi capabilities that we built into our robot. This way, we are able to send the motor commands and torque commands to our robots, and we are able to receive encoders and IMU data back into our system. Interestingly, we observed that the IMU readings were noisy, so we introduced using of the global positioning system using OptiTrack, which allowed us to have a position of a non-noisy position at all times. All in all, we are able to develop a clever way to run the control policy at a reduced computational costs, and we are able to test it in simulation and implement it on hardware. Thank you.